Yeah, so you want to get started on these? These should be hopefully they'll be fairly straightforward, because like I said, if you know Pivner, you basically got this thing nailed. It's just a lot of just moving the different values around and setting up what it is you want to solve for. So it's just algebra. So if you're good at algebra, if you're not so good at algebra, it might be painful. Hopefully we'll all be good at algebra by the end of this. So should we just like start with number one? We'll just do number one, and then you guys could have a look. Did everyone had a chance to look through them and see what's there?
Post it, because it's not posted on Canvas.
It's not posted?
No.
Oh man, well let me take care of that. Oh, that's stupid. Sorry about that. I will share the screen of me posting it. Okay. I did not realize. Okay. It should be in there. Yeah, if you don't have it, it's going to be kind of difficult to do it. Let me see. Oh my God, you're absolutely right. Okay, let's take care of that. Oops. I apologize. Sorry about that. There we go. Yeah, this recitation 9. Let's get that there. Yeah, so at least you guys can follow along to what the hell we're doing.
And I have a question. As far as the lecture exam goes, it's still being graded, right?
Yes.
Okay.
Oh, spring. I don't want spring. I want summer. Summer recitations. There we go. All right, there it is. There, you should be able to get it now. If you want to go and get it, I'll give you a few minutes to download it, have a look at it. Okay. Yeah, sorry about that, man. I said, yeah, I'm having trouble keeping everything together. Everyone's just so busy. Just trying to keep the Canvas page updated. It's a lot of work. Let me go back. Oops, not what I want. Okay, there we go. So is everyone able to find it now? Yeah. I apologize.
I found it.
Okay. Yeah, you can see how well organized I am. These things will happen from time to time. Yeah, why don't we just start with the first one then, and then while you're finding it, you can once you get it, you can scroll through it and see which ones seem strange. This is a very basic question that you'll come across, and with any of these problems, like I said, basically all you're going to be doing is taking our good old friend PivNert and just rearranging it into seeing what information do you have, what information is being requested, and what's the final answer supposed to be. And so you can see in this particular instance, the final question is, what is the volume? So if that's the situation, basically what we want to do is solve for volume. And so volume would then be equal to nRT divided by P. The other way we can look at it is because we're going to be changing one thing to another thing, we want to basically have one side equal to the other side. And in that instance, we can take advantage of the fact that R is always going to be constant. And so if that's the case, then we basically isolate R. And so PV divided by NT is going to be equal to R. Now, what does that actually mean? It means whatever my pressure, whatever my volume, whatever the moles and temperature, if I change them, if I divide PV by NT, it's still going to equal R. So basically, what that means is that my initial pressure, my initial volume, my initial number of moles, and the initial temperature will always equal the second pressure and the second volume and the second number of moles and the second temperature. They'll always equal each other because it's a constant. That's what a constant basically means. It means those things are always going to be related and give you the same value. So if we use this particular way of going about it, we can just plug in, let me undo that. Just plug in what our initial values are and what our new values are. So our initial values. So I have 30, so V1 is 30 liters. Our initial temperature is 200 degrees C. And our pressure is the same. So P1 equals P2. So
isn't it T1 for 200? Isn't it T1 for temperature instead of V1?
No, it's 200 at the beginning, and then it's 1 at the end. Oh, sorry, T1. Duh, you're absolutely right. Yes, T1. T1 is 200 degrees and T2 is 0. P1 equals P2, so we can take that out.
P2 is 1, right?
We don't know what the pressure is. All we know that it doesn't change.
T2 is 1, right? T2 is 1.
Oh, 1. Man, I'm off my game today. Yes. 1. So we've boiled it down to, we've taken out P because that's constant, and we haven't changed the amount of oxygen. So N is going to also be the same. So what are we left with? We're left with V1 divided by T1 is going to be equal to V2 divided by T2. And that's Boyle's law, right? I mean, that's basically all we're doing is changing the temperature, so we're going to change the volume. And so we just plug those in. Yeah.
How you know N1 is equal to N2?
Because we haven't changed the amount of oxygen. It just says if 30 liters of oxygen are cooled.
Okay.
So basically we have 30 liters of oxygen. We haven't added any. We haven't taken any away. And so our moles of oxygen are the same. So we can eliminate those as well. We don't know what it is. We could figure it out using PV NRT. We could figure out how much oxygen there was, but that's not the question. And if it doesn't change, we don't really care, because all we're interested in is the relationship between the volume and the temperature, because both of those two, the other two things change, or the other two things are constant. So if our pressure is the same and the number of moles is the same, we can basically ignore them and just focus on the relationship between volume and temperature, okay? And that gives us this relationship right here. So that's why I always just start with PV NRT. I just write that down. Pretty much all gas law questions, I just write that down, and then I figure out what is it I'm being asked. What is it that I need to know? And in this particular instance, I don't need to know what the pressure is, and I don't need to know what the number of moles are, because they stay the same. So I don't need them. So I'm not gonna bother calculating with them.
So if it doesn't mention moles, then it's constant. We assume that it's constant.
No, if it says if I had twice as much oxygen, something like that, if I added 3 times as much oxygen, or I let half the oxygen out, then without knowing how many moles, you could just plug in, and original is 1, N1 is 1, and N2 is like either half that or twice as much as that or 3 times as much as that, without actually knowing the actual amount of moles. You just know that it's more or it's less, and that will affect your answer. Because if all you're answering is the volume, if it's not asking specifically how many moles or how many grams or whatever, if the question doesn't involve the amount, but it just involves the volume, you don't actually need to know how many moles there are. You just need to know the change in them. Does that make sense?
Yes.
If you don't specifically need to know, if the question doesn't come down to how many moles are there, it doesn't matter the exact number. It just matters the ratio. Because as we know, with all the gas laws, they're either directly related or they're indirectly related. So the relationship is really straightforward. And so if it goes up by 2, we know that either, something's going to go up by 2, or something's going to change by 1/2, depending on whether it's a direct relationship or indirect relationship. So in this instance, my pressure is the same, moles are the same. So the only thing I need to worry about is what's the relationship between volume and temperature. And if I can't remember whether or not it's direct or indirect, I just write out PivNert and move things around. Then I see, oh, right, I divide one by the other, or I multiply one by the other. And in this instance, they're directly related, so I divide one by the other. So what do I have to do here? I still can't plug my numbers into this equation. What do I need to do?
Convert the Celsius to Kelvin?
That's right. That's right. That will matter. That matters a great deal, because the difference between 200 and 1 is 200 times, and that's a huge difference. But if I convert it to Kelvin, it's not as big a difference. So what's going to be T1? How do I convert Celsius to Kelvin?
Add 273.
Yeah, I just add 273 or 273.15. Either way, it won't make a whole huge amount of difference. So my T1 instead will be 473.15 Kelvin, and my 1 degree will be 274.15 Kelvin. Now I can plug everything. Now I have all the difference I need. And so my V1 is 30 liters. My T1 is 473.15. V2, I don't know what it is. And my T2 is 274.15 Kelvin. So basically I just multiply 274 by 30 and then divide by 473. So in other words, V2 would be 30 liters times 274.15 K divided by 473.15 K. K's go away, my temperature goes away, and I'm left with units of liters. So what do I get?
17.38 liters.
Okay, excellent. 17.38 liters. Now, is that going to be the final answer?
No, you have to take into account the significant digits.
Yeah, you do. And this one's tricky. This one was written poorly. On a test, I would pay more attention. Because how many significant digits are there in the temperatures?
3, 1.
One. There's only one, right? So yeah, I had a student a couple terms back who just gave me hell all the time for significant digits, because he was smarter than me. And so, yeah, so he would point this out. He said, well, professor, the actual answer would be 20 liters. I'd have to like growl under my breath and say, well, he's right. So what I would do in this particular instance is I would have like 200 like decimal and like maybe 1.0, something like that. So you have at least two significant digits. But remember, when you add 1 to one significant digit to something that has 5, we'll have 3 significant digits there, right? Because we've added 273 to it. So we have 3 significant digits there. And we've added 200 to 473. So we actually have 3 significant digits there. So the answer would be 3 significant digits. So the final answer would be 17.4.
Professor, for this is 5 significant, or you do not count the 1.15?
No, remember when you add two numbers, you look at the significant digits past
Okay.
the decimal. So I can't have any numbers past the decimal because my 1 doesn't have any numbers past the decimal. But so 273 point whatever, the whatever goes away. But I can have 274, and that has 3 significant digits. But yeah, I'll try and make it a little more obvious.
So would we use the
Yes.
liters in this case for significant digits?
Yeah, there's 3 significant digits there, so I'm probably, yeah. But it is true that when you add those two, remember, I think I gave you a question on the last test about adding and subtracting significant digits. So you should remember that. But in the pressure of a test, you may forget that's true. And I obviously forgot that was true when I put the question together.
Okay.
All right, yes, 17.4. And then basically to go back and double check your answer, does that make sense? So I've cooled the oxygen from a high temperature to a low temperature. So my molecules are moving more slowly. The pressure is the same. What's going to happen to the volume? The volume's going to go down. So yeah, that makes sense. The volume should decrease if the temperature decreases. So here, basically the same sort of question with the difference that we've changed the pressure. And so we'd have to take that into consideration.
And we need to change ml to liter?
Yes.
Okay.
Yeah, the standard methods for measuring these things: atmospheres, liters, Kelvin, moles. Although with pressure, actually with pressure and volume, basically all you're doing is just dividing by something. You're not adding anything. So if you're just looking at ratios, it actually wouldn't matter. But if you're trying to calculate something with R, like basically look at if I just wanted to see what the difference was between V1 and V2, it doesn't actually matter if I use milliliters or liters. It doesn't, or quarts or gallons. It doesn't really matter. Same with pressure. If it's in millimeters of mercury, or whether it's in torr, or whether it's in kilopascals, that doesn't matter. But T1 and T2 matters a great deal, because when I convert those, I'm not multiplying by something. I'm not multiplying the top and the bottom by the same number. I'm actually adding a number to it. And so this changes depending on whether it's Celsius or Fahrenheit or Kelvin. So that matters. Pressure and volume, the ratio won't change because I'm multiplying the top and the bottom by the same number. But it's a good thing to do, because anytime you're going to try and plug R in, you have to have liters, atmospheres, Kelvin, and moles, or else the calculation won't work. But ratios will work, except for temperature. So, but don't get too caught up in that. I was just answering your question. Sometimes it matters and sometimes it doesn't. But it's generally a good idea. If you're worried about it, just change everything to the right quantities and you won't have any issues. So shall we do this one?
Yes.
Okay, so where are we going to start?
Figure
Convert.
out what's given.
Yeah, we can start that way. Let's start that way. So figure out what our initial conditions are, what our final conditions are. So sample of gas occupies 1,400 milliliters. So V1 equals 1.4 liters, right? We just divide that by 1,000 or multiply by 1 over 1,000. T1 is 25 degrees and P1 is 760 millimeters of mercury. And then we look at our second set, and N1 equals N2. This is a sample of gas. So basically, it means we haven't added anything, we haven't taken away anything. It's just a sample of gas. So that's not going to change. So what volume will it occupy? So V2 is unknown. V2 is X. Same temperature. T2 is the same. So this time only the pressure is different. So I'm keeping my moles constant. I'm keeping the volume constant. I'm only looking at the pressure. So this time we're just looking at the effect of volume and pressure. Okay. So my P2 is 380 millimeters. So if we can't remember what the relationship is between volume and pressure, we can work that out using our good friend Pivnert. So we want to look at, we want to take away volume and pressure. So let's, again, we'll isolate R. So PV divided by NT equals R. So P1 V1 divided by N1 T1 will also equal P2 V2 divided by N1, oh, N2, T2. Now, we know that N1 and N2 are the same. Oh, and we also know T1 and T2 are the same. So what that tells us is what we need to do is multiply P1 and V1 together and multiply, and that will equal P2 and V2 together. And when you multiply two things together, does that mean they have an inverse relationship or a direct relationship?
Direct.
Reverse.
Inverse, right. Because as one goes up, the other one goes down. So if my P gets bigger, my V has to get smaller. But when I multiply them together, it will always give me the same result. So if P goes up by 2, V goes down by 2, it would equal the same thing. If P goes down by 4, V goes up by 4. Always going to equal the same thing. So all I have to do is multiply the two of them together. So I have to, oops. So I know, now I don't even have to calculate T1 and T2 because it doesn't matter, they're the same. I don't have to calculate how many moles there are either. What do I have to do?
You have to isolate V2.
Right, let's do that. So V2, oops. So how would I do that? How do I get V2 by itself?
B1 multiply V1 divide by B2.
So if I divide both sides by P2, then that goes away. Yeah, right. And I'm left with V2 equals V1 times P1 divided by P2. So I've got my two pressures here. Now, I don't need to convert them, really, but it probably wouldn't be a bad idea. Because why don't we have to? Because basically the ratio of P1 to P2 is going to be the same whether I convert it or not. Because I'm going to be multiplying them or dividing them or whatever by the same number. But if, again, like I said, if we don't remember that in the heat of a test and we're freaking out, I need to convert everything. Well, let's just go ahead and convert everything. It's not that much trouble. How do we convert P1 and P2 to atmospheres?
Multiply it by 1 atmosphere over 760 millimeters of mercury.
I like the way you think. I like how you didn't say divide, because you know I yell at you every time you say divide by anything.
So
Very good. Excellent. Right. So my P1 is just 1. P1 is just 1 atmosphere. That was easy enough. And P2, shockingly enough, looks like half an atmosphere. Right? 380 divided by 760 is 0.5, I hope. 1/2.
Yep, that's right.
Okay. So after all that, we come down to erase all this stuff. So V2 is equal to 1.4 liters times 1 atmosphere divided by 0.5 atmospheres. So what's my final answer?
2.8 liters.
Yep. And you could, since it's 1,400 mils there, you could also say 2,800 milliliters. Obviously, both are correct because they're both the same number. And they both have 2 significant digits, right? So either one is the correct way. 2,800 with a decimal on it would be wrong because we don't have that many significant digits. But 2,800 without the decimal, that's fine. So right, 2.8 liters. And we think, when we think about it, that makes sense. Our pressure's gone down by a factor of 2. So our volume's going to have to go up by a factor of 2. And that's exactly what happened. Okay.
How you get 0.5 ATM?
Oh, because the 1 atmosphere, this was 760 millimeters of mercury,
Mm-hmm.
and this was 380 millimeters of
Okay,
mercury.
gotcha.
And we just converted them to atmospheres. But you can see how we didn't really need to do that, because we just divide 380 and 760, we're going to get the same ratio. So,
in the test,
yes.
would you like us, like in this scenario, for instance, we didn't have to divide it. So on the test, would you want us to divide it?
What do you mean? You wouldn't have to divide? Oh, you mean you wouldn't have to convert it?
Exactly, to atmosphere?
No, if you're smart enough to realize you don't need to convert it, then I don't care whether you convert it or not.
Okay.
If you get the right answer, if you show me the steps and you put 760 up at the top here and 380 at the bottom there, and then get rid of millimeters of mercury. Yeah, I mean you don't have to convert them if you don't have to convert them, basically. But notice that none of the first 2 questions we've done, neither one of them have involved R. And so we haven't had to convert either the volumes or the pressures, because we've only been interested in the ratios. You always have to convert temperature, because then you're adding, you're not multiplying. And so that screws up the ratio. Because remember, the first question was like 200 degrees versus 1 degree. Well, that's a ratio of 200. But then when we added 273 to it, the ratio was like less than 2 to 1. So that makes a huge difference.
Okay. And define it and
All right. So great job so far. Yeah, you can see these aren't so scary. Just use PivNert, move this stuff around, you're good to go. Yeah, so this is just third one, basically is change in temperature and pressure. So we could, we'll do this one together, and then I'll let you look through the rest, okay? So, same, always set these up exactly the same, so then I feel comfortable with what it is I'm trying to figure out. So, I've got a bunch of things happening. So the temperature and the pressure at the beginning are 4 degrees and 3 atmospheres. So my T1 is 4 degrees. My P1 is 3 atmospheres. And it rises, and my initial volume, my V1, is 2.1 mils. Now, my T2 is 25 degrees.
Would you use Charles law?
Well, it looks like we're changing 2 different things here. So we have to use both, because the pressure is now different too. So my P2 is now also different. The P2 is now 0.95 atmospheres. So I can't use just one law, because each law takes care of just one relationship, between, we've got 4 different things: volume, pressure, temperature, moles, and each law shows you a relationship between just 2 of those. Now we've got 2 things changing, and so we need to know the relationship of both temperature to volume and pressure to volume. So we need to take both into consideration. So in order to figure this one out, and what about N? N1 and N2. Do we know what those are?
Would it be constant?
Yes, because it's a bubble. Supposedly, if no more gas gets into it, no more gas is released from it. It doesn't pop. I mean, if it popped, it'd be a pretty boring question. The final volume would be 0. But it didn't pop. The question is it going to get bigger? Is it going to get smaller? So N1 equals N2. So I just go back to PivNert. And I know I keep R constant. So P1 V1 divided by N1 T1 is going to be equal to P2 V2 divided by N2 T2. So what do I know? So N1 and N2 remain the same. So basically, I'm left with P1 V1 divided by T1 equals P2 V2 divided by T2. And what I want is V2. I don't know what V2 is. So how am I going to isolate V2?
Well,
What's
first,
V2 equal to?
wouldn't you first have to change the temperature to Kelvin and then?
Yes, when we plug everything in, we're going to have to change everything to Kelvin. But right now, I just want to figure out what I'm going to need to figure out what V2 is based on this equation.
Wouldn't it be P1 V1 times 2 divided by P2 T1, so you can isolate V2?
Right, so yeah, basically I would multiply P1 V1 by T2 P2.
P2 over P2, right?
Oh, I'm sorry, yeah,
P2 over
T2 over P2, yes.
Got T1 under.
T2 over P2 with T1 down here. Yeah. So basically what that's telling me is that I need to find the ratio of P1 to P2 and the ratio of T2 to T1. And then that'll give me, now I just plug everything in. So let me get rid of some of this stuff.
So temperature to Kelvin.
Erase.
Celsius to Kelvin.
All right, let's plug these things in. Yeah, would have been easier just to. Okay, so V2 is equal to. So what is my P1? So the pressures have already been.
3. Wouldn't you
So
have
P1 is 3.
Celsius first?
Yep, we're going to get there. So 3 atmospheres times V1, which is,
0.
the initial is 2.1 mils. And we can change that to liters if you like.
0.0021.
Times T2. And so T2 is 25 degrees C.
Oh, you're missing 1 0.
0, yeah.
Oh, I'm missing one?
So it's 0.
0021. Yeah, you're right. 0021 liters. Although we'll find out it doesn't really matter. I could have left mils there, but yes, you're right. So my T2 is 25 degrees C. So what's my, what temperature do I actually use?
25 times 23
Plus.
plus 23.15. 273.15.
Yes. So what do I put in here?
277.
You sure? I want T2.
Oh,
Remember, I want T2 on top.
298.15.
Right. 298.15 K. And then I divide all of that by my P2 and T1. So my P2, the second pressure, 0.95 atmospheres. And I multiply that by my initial temperature, which is 4 degrees. So what's my actual temperature in Kelvin?
277.15.
Yeah. Oh, 7, right, 0.15, okay. Okay. Now, always make sure we have the right units. So atmospheres, Kelvin, and we're left with liters. So that's good. So then we just do the calculation. So what do we get?
0.0071.
Oops. Oh, damn it.
But you have to take into
So 0.007, did you say? 713 liters. So we want 2 significant digits. So it would be 7.1 milliliters. So you see that the pressure has a much bigger effect than the temperature, because the temperature only changes by a factor of 300 divided by 275. That's not much of a change in absolute temperature. But the change in pressure is great. The change in pressure is more than 3 times. And so our bubble basically gets bigger by 3.5 fold.
So on the test, would you want us to leave it in liters is fine, or do you want how the question is worded?
It just says calculate the final volume. It doesn't say in liters, it doesn't say in milliliters, it just says calculate the final volume. So if you gave me the answer 0.0071 liters, that is correct. I can't say it isn't, right? Because these two are the same thing. So if it doesn't say, give the final volume in milliliters, feel free to give whatever units you want. You give it in gallons if you wanted to. It just says calculate the final volume. Yeah, so don't overthink it. If you have a volume and I ask for a volume, that you're good to go. Yeah, if I give specific instructions about units or something, then do that. But if I don't do that, then yeah, you're free to give whatever units you want for volume. Like gills or something. I know imperial measurements of so many bizarre units in them. I think gills is a unit of volume. All right. So who's had a chance to look through the rest of them? Is there one in particular that interested you?
Do number 5.
Sure, we can do number 5. Well, I'm not going to do number 5. You're going to do number 5. Oh, here we go. Yeah, so, yeah, basically you have no information on this one. All you know, that the pressure has gone up 3 times. And the absolute, so there's a good point right here. What does that mean? Absolute temperature is quadrupled. What does that mean?
Isn't it 273.15 Kelvin, and then you're just going to multiply it by 4? I'm not sure.
Well, negative 273 Kelvin is 0, absolute 0. But if it says absolute temperature, what units are those? Because it doesn't say, right? I mean, could absolute temperature in Fahrenheit, in Celsius, in Kelvin? It doesn't say. But if it says absolute, that has a very specific meaning. What do you think it means? well, think of it this way. In which way we measure temperature do we even use the word absolute?
Celsius.
Nope.
Zero.
Now, which temperature scale actually uses the word absolute?
Kelvin.
Kelvin. Kelvin's the only one that actually uses the word absolute. And it's absolute because there's no negative temperatures. So everything is on the same scale. If I'm dealing with Celsius, for instance, and I'm looking at the difference between minus 20 and plus 20, I can't say that it's doubled or tripled. It doesn't make any sense. If it's doubled, that means it's gone from minus 20 to minus 40. That's not true. If I say it's tripled, then it would go to minus 60. That doesn't make any sense. The only temperature scale where that makes any sense at all is Kelvin, because it starts at 0 and goes to, infinity or wherever it goes to. So whatever number I pick on this, like 5, and I compare 5 to 100, I can absolutely say that that has changed by 20 times. I can't say that on any other scale. Like, for instance, the difference between the boiling point of water goes from 0 to 100. Well, if I divide 0 by 100 by 0, I get infinity. I can't say that the boiling point of water is infinitely higher than the freezing point. That doesn't make any sense. So absolute only refers to Kelvin. That's the only place you can use it. Okay. So that one was a bit of a head scratcher when it says the absolute temperature is quadrupled. That means when you divide one temperature by the other temperature, you get a factor of 4. And you can't say that for sure with any other temperature measurement. Only Kelvin can you say that. So what does that mean? So we've got we have P1 and we have T1, and we're looking for V2, right? So we have a gas sample, so N1 is going to equal N2. So that's not going to change. We know that P1, the difference between P1 and P2 is 3 times. So P2 is 3 times P1. And T2 is 4 times T1, right? That's tripled and quadrupled. Is that right? And V2 is, we don't know what V2 is. Basically what we're looking for is what's the difference, what's V2 divided by V1? That's the question, right? By what factor will the volume of the sample change? So we're looking for what's the ratio of the final volume versus the initial volume. So how are we going to figure this one out? We don't really have any numbers to deal with. Well, start with Pivnert. Always go to Pivnert. And then basically, you're just going to get used to this relationship. P1, V1, and 1, T1. P2, V2, and 2, T2. So my ends are the same. Now I just start putting numbers in, basically. So what am I going to put in for P2?
Three.
Yeah, 3 P1. So we can just put in, so basically we can substitute P1 for 1 and have P2 for 3. We can do that. Actually, that might even be easier. That makes our math easier. That's a really good point. Why don't we just do that? So if P1 equals 1, And we don't even, because remember, we don't need to know what the actual number is. We just need to know what the difference is. So if P1 equals 1, P2 equals 3. That's a really good way of doing it, actually. And if T1 equals 1, then T2 equals 4. That's very clever. Good job. So that basically eliminates P1 and T1. We can just take those out. And what are we left with? We're left with P2 equals 3. So I'll take that out. And T2 equals 4. So, oh, damn. So where does the 3 goes on top and 4 goes on the bottom? Is that right? This is where P1 was? Or P2? P2 is here, right? Yes.
Goes on top, 4 goes on
P2 goes on top and T2 goes on the bottom. And my T2 is 4. And so I want this, my relationship between V2 and V1
4
is
divided.
going to be 4 divided by 3. So let's have a look and see if that makes sense. So if the absolute temperature is quadrupled, when the temperature goes up by 4, the volume should go up by 4, right? Because they're directly related. But if the pressure goes up by 3, the volume should be divided by 3 because they're inversely related, right? So 4 divided by 3, that makes sense. That makes sense because the temperature increases it by 4 times, but the pressure decreases it 3 times. So by what factor will the volume change? 4 over 3. That makes sense. So there's a number of ways you could do this. Either you could show me the 2 laws showing that pressure and volume are inversely related. So the change in times 3 by 1 is of 1/3 to the other. And then temperature and volume are directly related. You could do it that way. Or I just like doing, just writing out PivNert and just figuring out from there. Because if I do that, I don't need to memorize anything. Because I don't like memorizing things. I had a physical chemistry professor in college he was hard ass, but he made me understand something. Basically, he wouldn't let us use a cheat sheet. And you know how many like formulas there are in physics. My God, there's like 1 million of them. But what he told us to do was just know 2 of them and then just be able to derive all the other ones. And that was really good advice. I mean, I hated him for it at the time, but it was really good advice because I didn't have to memorize everything. I just had to know basically 1 law, and I could, just move it around and figure out all the other ones. And it helped me understand the material a lot more. Because if I just memorize a bunch of formulas, I don't really know what they mean. They're just stuck in my head. But if I have, PivNert there and I understand how all the things fit together, when I derive it myself, I can see, oh, right. I understand how that makes sense. If you just memorize the laws, they're just basically formulas. You plug numbers in without thinking. So you can take either approach, but I just think memorizing PivNert and then just going from there is probably the best way to do it. But some of you who are much younger and smarter than I am can memorize Charles' law, Avogadro's law, know how all the numbers go in. I can't. I don't remember what each of them are. I just remember PivNert.
So for this question, I should mention V2 is equal 4 over 3 multiply V1, or V1 is equal 3 over 4 multiply V2.
Well, it just says by what factor will it change.
Oh, okay, so 4
So
over
either way, you could just say that V1 is going to be
4 over
3/4 of V2, or V2 is going to be 4/3 of V1.
Okay.
It's the same It's the same thing.
Professor, how did it become 4/3 when you can just like flip it, or there's
Oh, it's basically, so here, this, we've got 4 V1s equal 3 V2s. So the relationship between, so if we divide, yeah, so if we want V2 divided by V1, then we divide both sides by 3.
okay.
Can we do question 10?
Sure, we can do question 10. I don't know what question 10 is, but let's have a look at it. 6, 7, 8, 9, 10. Okay. Yeah, so here we go. It's going to be a limiting reactant problem. So basically we need to figure out how many moles of reactants we have and how much product we're going to make. Here in this instance, it's actually telling us what the limiting reactant is. It's telling us the limiting reactant is, what is that?
MnO2.
What is it?
Mass?
No, just what is it? What do we call that?
Magnesium dioxide.
Nope. It's not, this is an ionics, it's got a metal and a non-metal.
Magnesium.
We use that, and it's not magnesium. What is it?
Manganese oxide.
Yeah, manganese 4 oxide, actually. Yeah, manganese oxide. I did a lot of experiments with manganese in grad school, so I have a special relationship with manganese. So, manganese dioxide. Oops, no, manganese oxide. So we know we're going to have basically an excess of this, because it basically says if you have that much manganese oxide, that is going to be the limiting reagent. So we can just assume we have unlimited amounts of HCl. So basically all we need to do is figure out how many moles of manganese oxide we have, and do we have a balanced equation? That's important. And how many moles of chlorine gas are we going to make? So first thing to do, how many moles? Well, first thing to do, actually, do we have a balanced equation? I always check that first. Is this balanced? I have 1 manganese on each side, so that's good.
Because you have to do 2 Cl. There's 4 Cl.
Right, there's four chlorines on as reactants. How many are there as products?
We have already Cl2 and Cl2 in the product, so
So
it's balanced.
are the chlorine atoms balanced?
Yeah.
Yes. And what about the hydrogen and oxygen?
Hydrogen is 4,
Mm-hmm.
and in the other side also 2H2 is 4.
And what about oxygens?
It's also because
2.
O2 and in H2O multiply 2. So it's
2. So everything's good. So we're good to go. So the very first thing we need to figure out is what? So here I'll write down the information I've got.
the mass is 12.
I have 12 grams of MnO2. What do I do with that information?
Change it to moles number.
Mm-hmm. Yep. So I'm going to multiply it by something to give me moles. What am I going to multiply it by?
Molar mass.
Mm-hmm. Now, do I multiply by the molar mass or multiply by 1 over the molar mass?
1 over.
Right, because I want moles on top and grams on the bottom. So someone looked up the molar mass of MnO2?
86.9368.
9368. 6, 8, so let's say 7. All right, so 86.937 grams. Okay. So how many moles does that give us?
0.13803.
Okay, moles. All right, so now we have this many moles. What's the relationship between moles of manganese oxide and chlorine gas?
Equal, because 1 to 1.
Yeah, 1 to 1. So I have 1, 1. So it's going to be equal amount. So that's how many moles. So my N, so when I do my Pivnert, my N Cl2 is the same, 0.1308 moles. So now pretty much have all the information I need to figure out the volume, because right now it's asking me what the volume is, right? So now I actually am going to need Pivnert this time. And it's asking me for volume. So my volume is just going to be NERT Piv, right? Because I just divide both sides by pressure, and it will give me my volume. This is what I want to solve for, volume. So that's going to be equal to, so I got my moles, so 0.13803 moles. What's R?
Constant.
0.0821 atmospheres liters over moles Kelvin.
Kelvin. Yep. And T is 25 degrees C. So what's 25 degrees C is what? When I convert it. Convert it.
It's 298.15.
Yep. 298.15 Kelvin. So actually, why don't I just move this over here? Need some space. All right, 0.13803 moles, 0.0821 atmosphere liters, mole Kelvin, times oops, 298.15 Kelvin, divided by pressure. And what's my oh, they did a nice thing. We don't have to do anything with pressure. We can just divide by 0.950 atmospheres. Now, this is where it gets tricky, because we're dealing with R that has these funky units, because there's 4 of them there, right? So we've got moles on top. So we were just looking at the numerator. I've got moles as a numerator, and I have moles as a denominator. So I can eliminate those, okay? I've got Kelvin as a numerator and Kelvin as a denominator. So now I'm left with atmospheres and liters on the top. I can get rid of moles and Kelvin, and I just have atmospheres on the bottom. So atmospheres are the only thing that's left on the top. Atmospheres are the only thing on the bottom. So the one unit that's left after all of that is liters. And that's what I'm looking for. So pretty much, that's why I always leave the units in there, because if I cancel them all out and I'm left with the right one, then I pretty much can figure out that I probably set up my equation correctly. And in this instance, only thing that's left is liters, and I'm looking for volume, so I'm probably good. And the other thing, if you're doing this on a test, and like I said, if you screw one of these numbers up and you get the wrong answer, it's not that big a deal, because I've seen that you've set it up properly. And so you're going to get most of the points. Yeah.
Can you go back to 0.082? How you get this ATML?
That's R. That's the value of R.
Okay.
This is the value of R, and the units of R are atmosphere liters divided by mole Kelvin. Remember when we did the lab yesterday, we plotted mole Kelvin against atmosphere liters. We got the slope, and the slope is the value of R, because that's what R is. It's atmosphere times liters divided by moles and divided by Kelvin, temperature. Yeah, it's a weird one. Trying to get your head around it, because generally when we think about constants, they're just uniting two things, showing the relationship between grams and moles, or grams and liters, or something like that, or moles and liters, something like that. It's just two, but this one is four. So we have to make sure we have all four of them in there and make sure they're in the right place. So yeah, so when you look up R, if you Google what is the gas constant R, it's going to give you a whole bunch of different numbers. Look for the one that has atmospheres, liters, moles, and Kelvin, because there's a whole bunch, and they're all depending on what you measure the atmospheric pressure in. And it varies because of that. But look for the one that has 0.0821. That's the one you're looking for. So at this point, all we need to do is just multiply and divide all the numbers and see what we get. So what are we going to wind up with?
3.5568. Well, I rounded it off, but
liters, right?
yeah.
Right. So how many significant digits should I really give here?
3.
3. Yeah.
Not 2?
There's 3 here. There's 3 here. And when we do the conversion of temperature, we get 3 there as well, because we add 273 to 25. And when we add them, we end up with 3 significant digits. So that one's a little tricky. We dealt with that one before. When we just had 1 significant digit, we had like 1 degree. But when we added it to 273.15, then we had 3. So the answer would be 3.56 liters. Okay?
557.
Because it was 3.556.
Oh,
So we get rid of the 6, we round that up, the 5 up to a 6. Okay.
So, Professor,
C.
you want us, so we shouldn't convert 273.15, we should just do 273. Because then that would change the significant digits.
No, but I mean, I use the 0.15 because it's there. And I mean, that's the actual number. And you use it for the calculations, but you don't report it in the final result.
Oh, okay.
Yeah, because the reason for that is when you add 1 to 273.15, you get 274.15 for the calculation, but you can only report the first 3.
Okay.
Right? So, yeah, so use it. Like I always say, don't round anything until you get to the end. And I know that some of you, I forget who's doing all the calculations. You're doing a great job. And she always reports like the 15 digits she gets, which is perfect. Use them all, use them all till you get to the very end. That gives you a more precise answer. If you round things off too early, your answer can be way off because you've basically rounded, some things you've rounded up, some things you've rounded down. And it could make a big difference when it's like a multi-step process. So just use them all. Use as many as you like. And then at the very end of it, figure out what's the most significant digits I could possibly report. And for this question, it would be 3.
Can we do question 13?
I don't know, can we? We'll see.
Yes.
Okay. Oh, all right. The molar mass. Ooh, here we go. Molar mass. We should know what the molar mass of chloroform is. Anyone know what chloroform is? Put it on a rag. We'll see if we get the right answer. Chloroform is this. So we should get that as an answer. Let's see if we do. All right, so we have a sample. It weighs 0.389 grams in a flask. So we have our N1 is equal to 0.389 grams. That just tells us how much we have. Obviously, it isn't in moles because we don't know what the molar mass is, but we know what the mass is. So we can basically, we'll use that as a starting point. Our flask has a volume of 102 cubic centimeters, and the pressure is 728 millimeters of mercury. So obviously we're going to need to do some manipulations here, right? But we're going to need to do some conversions. So what conversions are we going to need to do?
Centimeters to liters, grams to moles.
Yeah, we need to convert. Well, actually, no, we can't do grams to moles. We don't know how many moles we have. That's the actual question.
So centimeters to cubic centimeters to liters, and then millimeters.
Yeah, and pressure. Yeah, we need to figure out what our conversion is from cubic centimeters to liters. So how many cubic centimeters are in a liter?
1?
The 1,000.
Yeah, there's 1,000. So yeah, a cubic centimeter is actually 1 milliliter. And so that is 0.102 liters. Now, what's my pressure? How do I convert millimeters of mercury to atmospheres?
I have to multiply 7 to 8 millimeters of mercury times 1 atmosphere over 760 millimeters.
That's right. So how many atmospheres do I have?
0.95789 atmosphere.
Okay, atmospheres. Oh, and we completely forgot about the temperature. Duh. Our temperature is 97 degrees C. So what's my actual temperature? My absolute temperature, I'll put it that way. It's my absolute temperature.
370.15 Kelvin.
370.15 K. So basically, remember, R relates the 4 different units we have for gases. And as you see, we've got 3 of them. So basically, we're going to be able to use R to solve for the last one. So if we've got good old Pivnert, basically, which one are we solving for? In this problem, which one of those things are we solving for?
N?
Yeah, we're solving for moles, right? So N is going to be equal to, I'm going to divide both sides by RT. So that would be PV over RT. So now all I need to do is just plug those numbers in. So let's do that. Hopefully someone has remembered all those numbers. Someone's written all those numbers down, I hope. All right, let's do this. So that's going to equal our pressure. What was our pressure?
0.95789 atmosphere.
0.95 what?
789 atmosphere.
789 atmospheres. And my volume was 0.102, right? Liters. And on the bottom, I've got R, and we know that's 0.00821 liter atmospheres over mole Kelvin times our temperature. What was our temperature?
370.15.
0.15 Kelvin. Right, now you can start getting rid of units. So on the denominator, I've got K is a numerator, K is a denominator. Okay, now I go up to numerators. Now I can compare numerators. I have numerators on the top and numerators on the bottom, so I can directly compare those. And I've got atmospheres, liters, liters, and I'm left with this weird unit called 1 over moles. Well, what is that?
Mole.
Moles. It's just moles. So I'm left with moles. And that's good, because that's what I want to be left with. So my final unit is going to be moles. Good. So how many moles do I have?
Zero 0.00325151 mole.
0.00 what?
32151 mole of chloroform gas.
0.03251?
Yes.
Okay. So we're halfway, well, not more than halfway home. So now I know how many moles we have. But that wasn't the question, was it? The question, what's our molar mass? So our molar mass is grams over moles, right? That's what molar mass means. And so we have a mass and we have moles. So I'm just going to put grams over moles because that's what molar mass means. 0.389 grams over moles. And that'll give me grams over moles, which is molar mass. So what is it? Let's see how close we get. The nice thing about this, we'll be able to check our answer.
It's 120.991571.
991571. Okay, I like it. How many should we be reporting though?
3.
3. Yeah, really we should be reporting 3. So we should be around 121. So what's the mass of chloroform? I think that's pretty close.
I got a different answer. I got 120.99145.
Oh, sorry, what did you get?
120.99145.
Oh, that's the same answer though. 120.991. I mean, it's 120.99, right?
Yeah.
Yeah, so pretty much the same answer. What's the actual mass of chloroform?
119.38.
I'd say that's pretty close, right? I put that down as a win. Yeah, so yeah, good job everybody on that one. I would say, yeah, if you're off by less than 1%, I'd say that's a pretty good job. And since we were, rounding things at the end, if we had a more accurate measure of the temperature, if we had a more accurate measure of the pressure, we probably would have got it even closer.
So we'll take 3 digits.
Yeah, so I'd say, so your answer would be 121, and you'd look and you see the actual answer is 119.4, and you think, well, that's pretty good. Hell, I'd take that in a lab, wouldn't you? I mean, if you were asked to calculate the molecular weight of something and you got to less than 1% error, I'd take that as a win. But yeah, because there's going to be uncertainty in the mass. If you only have 3 significant digits for the mass, for the volume, and the pressure. So, you can't really expect us to get any closer than 3 significant digits. If we had more, we could probably get that closer.
And
So realistically, it's as close as you're going to get.
and the unit is gonna be gram over mole or M, right? The unit.
Unit's going to be grams over moles. Yeah, because it's molar mass. That's what molar mass is, grams over moles. Yeah, right. So your official answer should be, 121 grams per mole. Good point. Yeah, you should have the number and you should have the units for the. All right, got time for one more?
Yes.
Let's pick a hard one.
Can we do number 4, please?
Ooh, going back. Number 4. Oh, we did that one.
It's the same as number 5.
Oh, you meant 5?
No, it's the same as number 5. It's just
It is the same as number 5. Yeah.
Okay.
Yeah, just do 5. Just do the same thing.
Can we do 8?
8, yeah, density.
Yeah, one I wanted to show you. Yes, that was the one I was going to show you because it doesn't make any sense, right? Like, I don't have any information. So basically, here you actually have all the information you need, but you have to make an assumption. That's the tricky part. So we're going to use PivNerd because PivNerd is our friend. We're going to use that, and we're going to make some assumptions because it doesn't tell you how much gas you have, right? It's just, I got some gas. How much gas? So we make some assumptions to make our calculations easier. And so what do we know? We need to figure out grams and liters for density, right? So grams, I don't know how many grams we have. But we can figure that out from the mass of chlorine gas. The mass of chlorine gas will tell us that. What's the formula for chlorine gas? The chemical formula.
Cl2.
Cl2, very good. Yes, Cl2 is chlorine gas. So basically, I could figure out my mass of chlorine gas, but I don't know how to figure out what the volume I'm going to use. But this should sort of tell you something. What do we know about the volumes of gases at standard temperature and pressure? All gases have a certain volume at standard temperature and pressure. You remember?
$22.4 liters.
Yeah, how much gas is a volume of that much? That's the important part. Yes, it's 22.4 liters, but 22.4 liters for how much gas? Not every amount of gas is going to be 22.4 liters. A very specific amount of gas is going to be 22.4 liters.
1 mole.
That's it. Yes, exactly. Standard temperature and pressure tells us that if we have exactly 1 mole, every gas, doesn't matter what it is, takes up about 22.4 liters of space. That's the volume. So if N equals 1, V equals 22.4. And that is the assumption we're going to use. So we're just going to use 1 mole because at STP, we know then what the volume is. So that's going to be that's what we're going to use to calculate our density, because that gives us both the volume and the mass. Now we're pretty much done because I know what my volume is going to be. My volume is going to be 22.4. What's my mass going to be?
1 mole.
Right, my mass is going to be 1 mole. But the question isn't moles per liter, is it?
It's grams per liter.
Yes. So I need to do something with that. What am I going to do with that?
Convert it to the molar mass of CO2.
Yes, right, because that will give me grams of Cl2. So I want the molar mass of Cl2, because I want how many grams in 1 mole of Cl2, and I'll get rid of moles and I'll be left with grams. So what is the molar mass of Cl2? Should be around 70 or so.
71 grams.
What is it?
71 grams.
Is that all? Is that all the numbers we have?
It's 70.906.
70.906. There we go. I always knew I could count. Who is it that's giving me all those numbers? I want to thank you.
Oh, it's Sandy.
Sandy. Great job. Right, because we want as many significant digits as we can, because we're going to be limited later. So we don't want to, this is sort of goes back to the point I made in the previous question. Don't round too early. Use a ridiculous number of digits. And then when you get to the end, you can figure out how many you need. So I got my grams and I got my volume. So now all I need to do, so at standard temperature and pressure, 1 mole of chlorine takes up 22.4 liters of space. And that is true for any gas. Well, as we learned yesterday, it's approximate. Some are going to be a little bit more, some are going to be a little bit less, but pretty close to 22.4. So a mole of ammonia, a mole of water vapor, a mole of xenon, a mole of neon, a mole of hydrogen, doesn't matter what it is. In this instance, we've got a mole of chlorine, which means we've got 70.906 grams in that mole. And our 1 mole takes up 22.4 liters. And then that's going to give us our density, just 70.906 divided by 22.4. So what's our density going to be?
Mass divided by volume.
Mm-hmm. What's our answer?
3.16544 grams over liters of
1654 grams per liter. Right. So close to pi. So how many significant digits do we give for this one?
3.
3, right, because we use 22.4. If you looked up, and that's pretty much all we can use unless you look up the actual molar volume specifically for chlorine. If you look that up, you could give this density a lot more accurately. Like if you looked up the density of actual chlorine gas and it said it was 22.22789, and you looked up the molar mass and you got it to within 6 digits, you could give a 6-digit answer. But since we're using 22.4, that's only 3 significant digits, so I would say 3.17 grams per liter.
Professor, just I want to ask you, so any gas at standard temperature, has only 1 mole, N is equal 1?
No, we're using the relationship of moles to volume at that pressure and temperature. What is standard temperature and pressure? Can someone tell me what it is?
Because I noticed you use the molar mass of Cl2, right?
Yes, yes, yes. So what is standard temperature and pressure anyway?
Is it 273.15?
Yeah, so it's 0 degrees Celsius, so 273.15 Kelvin. And what's the pressure? How many atmospheres of pressure?
One.
1, right. So the point is at 0 degrees C, or 273.15 Kelvin, and 1 atmosphere, 1 mole of all gases are equivalent to 22.4 liters. So we use that information. That's why this question is impossible unless I give you STP, unless I say it's STP, because there's no way to calculate. You don't know what grams or you can assume I have 1 mole. You could say that I'm going to start with a mole. Well, how many liters would that be? And so I could give you a precise temperature and a precise pressure, and then you could calculate the volume and figure out the density that way. But since it's standard temperature and pressure, it should automatically know that 1 mole is 22.4 liters. Because basically it's telling you that's my temperature, that's my pressure. So if you have moles and temperature and pressure, you can determine volume. So we could have plugged everything into Pivnert, but we didn't have to because it's standard temperature and pressure. So we just assume that 1 mole is equal to 22.4 liters and not have to calculate it. But you could still do the question if I gave you 2 other specific temperatures and pressures. You just would plug them here. You plug in the pressure there, you plug in the temperature there, assume 1 mole, and go from there. So do you see why we use 22.4 liters? We're still not clear on that.
I can see it.
Yeah, all gases have approximately the same volume at 0 and 1 atmosphere. So we could use that information to our advantage here. And I think there's another question very similar to that later, where it mentions STP. You should know what STP means. Because you may get a question, something like, I collected a certain amount of gas at STP. The temperature went up 25 degrees Celsius. What is my new volume? Something like that. And so you'd have to know that, well, I started at 0, and then I went up to 25 degrees C, convert them both to Kelvin, and then do the calculation. But so you should know that STP is 0 degrees Celsius, 1 atmosphere of pressure. That's gotta have that in the brain. Right. Any other questions before we call it a day? I think you can see how these work, right? Just basically manipulating the variables to get the variable you want on one side of the equation and all the other ones on the other side.
Let me see another question. Can we do 14?
Let's have a look at 14. Might be able to point you in the right direction. Okay, yeah, so this is just a Pivnert question. Of course, they're all Pivnert questions, but yeah. So this, remember, R relates 4 variables. And here we've got liters, so we've got volume. We've got temperature. And we got pressure. This is just a plug and chug question. Basically, all you have to do is convert temperature to Kelvin, convert pressure to atmospheres, and just put them into this equation and solve for N. And that'll give you the number of moles. And that's what the question is. How many grams of gas? So if you figure out how many moles of nitrogen you have, you can figure out how many grams of nitrogen gas you have. Just so 50 will be that plus 273, 3.15 K. Pressure will be this times 1 over 760. And liters, you don't have to do anything to. And your R is just 00821 atmosphere liters, mole kelvins. Yeah, just figure out moles. Just remember that there's 2 atoms, so it's the molar mass of nitrogen gas is going to be like around 28 grams per mole, not 14. That's a really common mistake that a lot of people make. Forgetting that chlorine gas is 2 atoms, nitrogen gas is 2 atoms, oxygen gas is 2 atoms, and so on and so on.
Can you give me an idea about question 9?
Okay, question 9, what's number 9?
Wait, before you go to that, for
Oh,
that,
sure. I'll go back to 14.
I just have a question. Once you find the moles, then do you have to convert the moles to the grams?
Yeah, because that's the question. The question asks you how many grams, doesn't ask you how many moles. So you calculate moles, and then you figure out how many grams there are from there. So Pivnert will give you moles, but it won't give you grams. So then you just do a, real simple conversion.
Okay.
Yeah.
To molar mass, yeah?
No, we're not asking for the molar mass. You use the molar mass to calculate grams from moles. Yes. So 9. Basically here we have 2 gases which are reactants, and so we've got basically the question is you've got 2.5 liters of that, and it's at 320 Kelvin and 680 torr. So basically you've got N, T, and P. So you're going to calculate N using Pivnert. So N is going to be equal to PV divided by RT. So you convert this to atmospheres. That'll give you moles. So then you go and figure out, if I have that many moles of nitric oxide, how many moles of oxygen am I going to need? And you realize the number of moles of oxygen is 1/2 the number of moles of nitrogen oxide, right? Because you need 2 moles of NO for every mole of O2. So however moles you figure out here of NO, you're only going to need 1/2 of that for oxygen. So now that you have oxygen moles, you have NO2, you go back and figure out what volume that would be. So this volume is gone. You have the same temperature, same pressure, and now you have N. Now you're solving for V. So with V is going to be equal to NERT divided by P. So that is going to be, oh, wait a minute, yeah. So now you plug in this, and the V is going to be equal to nRT divided by P. And you know what this is, you know what this is, you know what this is, and you've calculated that. That'll give you the volume. Yeah, basically, so this one you use PivNERT twice. One to figure out moles from volume, and the other one to figure out volume from moles.
Professor, what's that mean? 680 torr. Is that the unit of?
Torr. Torr is equal to millimeters of mercury.
Oh, okay.
It's the same,
The
it's
same
exactly the same
Oh,
thing.
okay.
Yeah. So in both instances, you multiply by 1 atmosphere divided by 760. Yeah, it's the same unit. It's one that, it's one we use in the lab frequently because it's just easier to say torr than millimeters of mercury. And generally, when you are measuring very low pressures, they're given in like torr, millitorr, microtorr. That really, like when you're pulling really strong vacuums, they're measured in torr, not so much in atmospheres.
And you said 1 mole of oxygen, it gives 1.5 of moles NO?
No, it doesn't give. It it's asking, the question is, if I have 2 moles of, that's what the balanced equation says. If I have 2 moles of NO, I'm only going to need 1 mole of O2 to completely react with it, because the ratio in the reactants is 2 to 1. So when you figure out how many moles of NO you have from the pressure, the volume, the temperature, you're only going to need half that much of oxygen. That's what the balanced equation is telling you. So let's say you have half a mole of NO. Well, you only need 1/4 of a mole of oxygen to completely react with it. And that's the question. Will react completely. So balanced exactly. All right, anything else, folks? We're going to start thermo tonight. Are you excited? I'm excited. Nobody else is excited. Fair enough. All right, any more questions? I will see you this evening. And anything else you wanted to ask before we go?
If you could post the video for Lab 8. please.
Yes. Yeah. Yeah. Tomorrow, actually, we'll have like 5 minutes to myself, and I'll put them up tomorrow.
Thank you.
Yeah.
And for part 2 from lab 7,
Mm-hmm.
Because we have 2 video for lab 7.
Yes, because we did it twice. Yeah.
Yeah.
Yeah,
Can
that'll
we
go up too.
second
Mm-hmm.
one? Okay.
Yep. Okay, we'll see you in a little while. And think thermodynamic thoughts. We'll see you then. Okay.